It's the far side, like Glenmore's. It's always fun. You see the chickens? It's what chickens with no bones would look like. It'd be very difficult to move with no bones. And it's kinesiology. It's like physics and biology put together. Okay? Without bones, your muscles have nothing to pull against, and as a result, you would not be able to exert any force, except to maybe twitch a little bit. So yeah, the next time you have a boneless chicken, it comes from the boneless chicken ranch. Probably not, but it. Okay, so we are going to start, okay, Unit 4 today. We won't get very far into it, but we'll go over kind of the principles of simple harmonic motion. Okay? Simple harmonic motion is very simply a motion that repeats itself over and over again. Okay? Like a pendulum. Okay? So a pendulum is a perfect example of simple harmonic motion. Okay? Once set in motion, the motion continues identically over and over again. Now, obviously in the perfect physical world. In the real world, it'll eventually stop. Okay? But it will swing through a fairly narrow arc pretty reliably for quite a while. That's why we use them to keep time for so long. Okay? They can do this oscillation over and over again because I'm not doing anything to it right now. Okay? And it's through that narrow, probably 10 to 15 degree arc there at the bottom, okay, oscillating pretty reliably without any help from me. And eventually it's going to stop, but it'll oscillate back and forth. Okay? The same would be true for our other type of simple harmonic oscillator, and that would be a mass on a spring. So if I put a spring down and I attach a mass to it and I push on the spring and then let it go, that thing will oscillate back and forth with the same motion over and over and over again, especially if it's on a frictionless tape. Okay, everyone kind of follow me there? All right. Now, for simple harmonic motion to happen, we are looking at some things that we're already familiar with. Forces and energy. Okay? If something's going to keep going back and forth and oscillating over and over again, does mechanical energy have to be conserved? It does. Okay? Otherwise it would stop, right? It'd be losing energy to something else, to the surroundings, sound, heat, whatever, right? And in order for that to happen, okay, for energy to be conserved, that means that we are converting potential energy into kinetic and back again, and that conversion just keeps happening, just like a roller coaster. Okay, same idea, but now it's going to be applied to the two types of simple harmonic motion. For a pendulum, it's identical to a roller coaster. What kind of potential energy does it have when it's out here?
Potential.
What kind of potential energy though? Gravitational. Okay. If I have a mass on a spring, what kind of potential energy is it? Elastic. Okay. So you guys thought I messed that up. Then I did, and then I realized I didn't. So there's two different kinds of potential energy. We've dealt with gravitational potential already, okay? But we are going to start looking at elastic potential now because we're going to be dealing with springs, okay? And anything that you can change the shape of that wants to go back to its original shape can store elastic potential energy. Okay. Now, if I'm going to have this object continue to convert energy into kinetic and kinetic into potential, okay, what keeps bringing it back? Like, I pulled it out to the side. What keeps bringing it back to the middle?
Gravity.
Gravity, okay, or at least a component of gravity that's acting along the arc that it's traveling, because gravity acts down, okay? That force we call a restoring force, because it's trying to restore equilibrium. This is where the pendulum would sit if I didn't do anything to it, right? It would just sit there in the middle and do nothing. That is its equilibrium or balanced position. A mass on a spring also has an equilibrium or balanced position. It's where it would sit if nobody bothers the spring. Okay? Once I disturb either the pendulum or the mass on the spring from that equilibrium position, it's going to require me to exert a force through a distance, which means I've done work. Okay? And when I let it go, the spring, or the component of gravity if it's a pendulum, is going to act back towards equilibrium. Problem is, forces cause objects to do what? Accelerate. So I disturb the pendulum from its equilibrium position and I let it go. Gravity, or the component of it along the arc, accelerates this thing. Is it going to stop at equilibrium? No, that's what causes simple harmonic motion. The restoring force never succeeds, except for a brief instant. It gets the object back to equilibrium, but when it gets there, it's just going right on through because it's been accelerating all the way there. Okay, so it goes right past, and then it's like, oh, start over again, because now we're going this way. Okay, and now the restoring force is pulling back towards equilibrium, which incidentally is the direction it always pulls. Okay, back towards equilibrium, but now it's slowing the pendulum down. Okay, when it gets to its highest point, it'll stop, and the restoring force will continue to bring it back, or start to bring it back, into equilibrium again. And because that restoring force can never kind of get the job done, okay, it's going to continue to oscillate back and forth as long as it doesn't lose any energy. Okay, so there's a lot of that stuff that we talked about in kind of Unit 2 and a little bit in Unit 3 with period and frequency that's going to be a part of all of this type of motion. Okay, so a playground swing is an example of a pendulum. Okay, and you can get a playground swing to go back and forth, but what do you have to do? Yeah, you got to pump your legs, right? Okay, back and forth, put the energy in there because there's actually a lot of friction up on the hinge there at the top, and it's losing energy. There's air resistance, there's all of that kind of stuff. Okay, but it's still a fairly good example of simple harmonic motion. Okay, mass on a spring, as we already talked about, and all of the musical instruments that we play also rely on simple harmonic motion. Something in every instrument oscillates back and forth, disturbing the air around it. Okay? The frequency of that disturbance goes along with the sound of the note that that particular string or reed or whatever is going to produce. Okay? That sort of makes sense? Okay? And if you play brass instruments, then it's the vibration of the lips. Okay? If it doesn't have a reed, okay, it's the vibration of the lips and the length of the tube that you allow the air to go through. So when you push different keys, you change the length of the air column that is going to vibrate. Okay, so we'll look at that quite a bit later on in the unit when we're talking about waves, but air columns are responsible for basically all of our musical instruments being able to work, even a guitar. Okay, if you have an electric guitar and it's not under power and you pluck a string, how much noise does it make? Not very much. Okay, but an acoustic guitar makes a lot of sound, okay? Because those waves go into the resonance chamber. It probably has a more technical name, but that's what physics calls it, okay? So the hourglass-shaped part of the guitar, okay? And the waves bounce around in there, and they interfere constructively, and they actually naturally, without energy being put in, amplify themselves, okay? So that we hear a louder sound. Okay, so back and forth, we got this thing oscillating, okay? That requires a restoring force, okay? And the restoring force is always attempting to restore equilibrium, okay? We measure everything in simple harmonic motion from the equilibrium position. So we will be talking about things like displacement, okay? That displacement is always measured from equilibrium, okay? We're 5 centimeters from equilibrium, or okay, negative 5 centimeters from equilibrium if we're on the other side. All right, and we said that the object is going to be moving fastest at equilibrium. Okay, it's also where it would sit at rest, but once it's moving, that's where it moves the fastest because the restoring force has been acting on it all the way to there. Now, this idea of the restoring force. The further from equilibrium I get, what happens to the restoring force?
The faster it goes? Or like further?
The further from equilibrium I get, what happens to the force? Like think about a spring.
More intense?
Yeah, it gets bigger. Yeah, right? If I'm compressing a spring, the more I compress it or the more I stretch it, the harder I have to pull. Agreed? Okay? You did this in Science 10. You did the rubber band thing with the little spring scale. Okay, or if you had it during COVID, you watched the video of me pulling the rubber band with the spring scale. It was very boring. Okay, but it's the same idea. The further I pull an elastic object, the harder I have to pull it. Okay, which means that restoring force gets bigger the further from equilibrium you get, linearly. That means at equilibrium, the restoring force is what value? 0. Okay, because at equilibrium, there isn't a restoring force. That's why the object would sit there. the net force acting on it at that position is 0. Okay? There is no restoring force at that position because it's where it wants to be. But the further from equilibrium we go, the worse it wants to get back, so the harder it's going to push or pull. And that is what is necessary for simple harmonic motion to occur. Okay? For simple harmonic motion to occur, the restoring force has to vary linearly with displacement. Okay? Now, this is where sometimes people get a bit confused, because does the force of gravity on an object change?
No.
No. So how is it then that for a pendulum, which relies on gravity as a restoring force, how can the restoring force get bigger if gravity can't get bigger?
There's less of an angular component of gravity.
Exactly. This is an arc. Okay? Gravity acts straight down. As soon as I move it away from its equilibrium position, there's a small component of gravity acting along the arc. When I get out to here, it would be all gravity, because along the arc, or tangent to the arc, would be straight down. Okay? But anywhere closer, gravity's still the same. Gravity still points straight down, but the part of it that goes along the arc gets smaller and smaller. Okay? So it can still vary linearly with displacement, but it's along the arc. That would require like calculus for us to calculate, so you don't have to worry about doing that. You just have to understand that it's not gravity that is the restoring force, it's the part of it that acts along the path it swings on. Okay? With a spring, it's easier, right? It's easier to picture. As I push on the spring is going to push harder. Okay, so this here, that is the basis for all simple harmonic motion. If simple harmonic motion is going to occur, then the restoring force has to vary linearly with displacement. And so the further from equilibrium we get, the harder the restoring force is going to push or pull. Oh, sorry. Too far. Okay, so this whole thing with gravity, I'm going to try and diagram it here for the pendulum. If I'm out here at the edge, okay, gravity would be acting tangent to the circle, and it would be at its full value. Okay, gravity is the same no matter where on this arc the object is. Okay, but it has a component that acts along the arc. Okay, here it's the full value of gravity. Okay, here it's a smaller component of gravity. Okay, here an even smaller component of gravity. Here an even smaller component, and so on until you get back to equilibrium, where it would be completely perpendicular and have no component in that vertical direction. Okay. All right. Everyone okay with that? Everyone got that highlighted in their notes or written down? Okay, so the motion of objects that are undergoing simple harmonic motion can be described with some things we're familiar with and one new thing. Okay, the things we're familiar with are period and frequency. Right? So the amount of time it takes a pendulum to go back and forth one time, or out and back one time, is its period. Okay, for a mass on a spring, out and back. Okay, is the time. The time for that is the period. Right, now, that's one oscillation. In one oscillation, you have to go through equilibrium twice. Once on the way out and once on the way back. Okay, so we often look at a cycle starting at equilibrium. Okay, so for this mass on the spring, okay, the mass goes out, comes back to equilibrium, goes out to the other side, and then comes back to equilibrium. That would be one full cycle. It went through equilibrium 2 times. Okay, we don't count that one because that's 0. Okay, everybody all right with that? What shape did that make?
Sine.
That made a sine wave. That's why waves and simple harmonic motion go together. When something oscillates with simple harmonic motion, it makes waves. Okay, we can make waveforms, okay, and those are things we can detect. Okay, so we got period and frequency, and then we got this thing called amplitude. Amplitude is how far, the maximum distance from equilibrium that the object will go. Okay? It'll go lots of distances from equilibrium along the course of its movement, but the furthest distance is its amplitude. Okay? So this would be the amplitude here, and so would this. And they would be equal. Okay? You go just as far in one direction as you do in the other. Okay? At least for horizontal. If it's vertical, it's different. Okay? Now, if we're talking about sound, amplitude has to do with what characteristic? Frequency has to do with pitch. Okay, so a different frequency has a different pitch. Okay, so if I'm listening to something that has a frequency of 200 hertz, that would be a very low frequency sound, deep bass. Okay, if I'm listening to something with a frequency of 2 kilohertz, that would be extremely high pitched. Okay, so amplitude has to do with what characteristic? What do you use an amplifier for? To make things louder. Okay, an amplifier increases the amplitude of the waves and thus their volume. Okay, the further from equilibrium you go, the more energy is required to do that because your distance is increasing. Same amount of force, but greater distance. Okay. All right, is that making some sense? Okay, so amplitude has to do with the potential energy and thus the mechanical energy that an object with simple harmonic motion can have. Okay. All right, so if we're talking about a pendulum, a mass on a spring, sorry. Okay, if we're talking about a mass on a spring, what two things do you suppose would affect the period? How long it would take that mass to go back and forth one time? What two things would affect it?
Amplitude?
Yes, but actually these two things would also affect the amplitude. You're absolutely right. I didn't word that very well. So period and amplitude and frequency and all of that stuff, these two things affect it. What two things would affect those things?
Work?
Yes, I'm still not wording this very well. I'm getting really good answers because I'm not wording it well.
Velocity would be one probably.
Again, has to do with kinetic energy. That has to do with potential energy. Okay, I'm thinking like properties, not so much. Yeah, man, you guys are thinking way outside the box, which is awesome. I can't even get the answer I want because of that. Maybe I'll just tell you. Oh.
The length of the spring.
Okay, also going to affect the amplitude. That goes along with amplitude. Okay, how long it takes to go back and forth is dependent on the two things that are doing the oscillating: the mass and the spring. See, it was too simple. You guys are like that. It was too easy, right? You guys were way over it. That's good though. Okay, are all springs the same? No, I wouldn't take the spring out of a ballpoint pen and put it on my car for the suspension. Okay, it would not work very well. Okay, similarly, I would not take the spring out of my car and put it in a ballpoint pen, or I'd have to jump on the thing to actuate it. Okay, so no, different springs work differently. They all have what we call a different spring constant, or K. Okay, and spring constant is measured in newtons per meter. It's the amount of force you would have to use to change the length of the spring by 1 meter. Okay, heavy springs would have very high spring constants. So the spring in your car, okay, that value would be very high, right? Probably thousands of newtons per meter. Okay, whereas the spring in a ballpoint pen, okay, is probably like 0.5 newtons per meter. Okay, it doesn't take very much to actuate it. Okay, and then the mass. I mean, it's just a matter of inertia. Once I get a big mass moving, is it harder to stop it? Yeah, it has more inertia, but it also has more energy because mass goes along with both kinds of energy, right? Okay. So if it gets moving, the more mass, the longer, the further it's going to go. It's going to have a greater amplitude. Well, that means that it's going to take longer to make one cycle. Okay, so the two things that affect the period of a mass on a spring are the mass and the spring.
Okay, and the formula looks like this. Okay, it's on your formula sheet, okay, but we can calculate the period of a mass on a spring by going 2 pi times the square root of mass divided by spring constant. This is one of the formulas I showed in my science 10s when I'm teaching them algebra, showing them how triangles will never work for them, okay, to do algebra. You guys aren't intimidated by this formula at all, okay? If I wanted to manipulate this formula to solve for m or k, what would I have to do to everything in the formula? I'd have to square it, yeah, because those are under the root, right? They're rooted, so I would have to square everything. So before you could manipulate this equation for anything other than t, you would have to go like this. T squared equals 4 pi squared m over k in order to get rid of the roots, okay? Everybody all right with that? Not hard after that to manipulate, but it certainly doesn't work with a triangle. Okay, it's just my point. Okay, so m is going to be the mass of the object, and that's going to be in kilograms. Okay, and the stiffness of the spring, as I said, is going to be in newtons per meter. All right, everybody okay with that formula and how it works? And we'll go over a couple of examples here, but it's not like going to tax you at all. Okay, so the period is the time for one complete oscillation. The amplitude is the maximum distance from equilibrium, okay, in either direction. And obviously frequency would be the number of times it goes back and forth in a second. Okay. All right, so as long as we know those terms, we're good, because we use those terms in all of the problems that we have to solve, so you have to know what they mean. Okay, so if I have a ball that is a mass of 0.2 kilograms attached to a spring that has a tension or spring constant, those terms are used interchangeably, of 28 newtons per meter, okay, the ball is released from its equilibrium position. How long does it take the ball to complete one cycle and return to its equilibrium position? All right, so I have the mass, 0.2 kilograms, okay, I have the spring constant, 28 newtons per meter, okay, and I just plug it into the formula. So T equals 2 pi times the square root of 0.2 over 28, and I would get that that would take just over half a second. Right, everyone okay with that one? Right, and manipulating that formula, like we said, square everything and then just start moving stuff around. It's not going to tax your algebra skills in any way. Okay. For a pendulum, what things are going to affect the period of a pendulum? Okay, mass.
Velocity.
Velocity is not, because velocity is going to change as it goes along here, right?
Right.
Yeah. Right? This one oscillates back and forth a lot faster than that one does. The period of the longer one is much longer than the period of the short one. Okay, what else?
Air friction or?
Okay, assuming that we're in the perfect physical world. Otherwise, yes, absolutely it would. What did we say was making this happen? Gravity. Specifically the acceleration due to it. Now, here's the thing with mass, because mass is always the first answer I get. But if gravity is making this thing oscillate back and forth, and acceleration due to gravity is one of the factors that affects the period, does mass affect the period? It doesn't, because all things fall at the same rate, regardless of their mass. But it's a gut reaction, right? Like we look at something fall, mass matters. Mass has to make a difference. Like it's going back and forth. Okay? If it's heavier, gravity pulls on it harder. That's true. But its acceleration is the same regardless. Okay? The force of gravity would be greater. That's what we think. That's why everyone says mass would matter. Okay? But it's the acceleration due to gravity that causes it to fall and follow that arc. So actually mass plays no role. Next week we'll do a lab where we'll prove it. Okay? We'll build a couple of little pendulums and you'll see that
Doesn't matter how much mass you put on the end of that pendulum, its period is exactly the same. We won't be able to test the effect of acceleration due to gravity, however. Yeah, because it would require us to go somewhere else, which is not in the budget. And the waiver for that would be so long. Okay, you know, it's okay for my son to get on this giant rocket and okay, so for a pendulum, okay, the two things that affect the period of a pendulum, the length of the pendulum and the acceleration due to gravity, which unless you're told otherwise is going to be one number, 9.81. Okay, actually very simple experiment done by astronauts when they got to the moon, okay, was just trying to confirm acceleration due to gravity and get some measurements that you know, the astronomers could use to kind of confirm that, you know, the composition, density, and things like that of the moon, was to take a pendulum there and get the true acceleration due to gravity on the surface. Okay, super simple experiment. They just had the thing swing back and forth and they timed it. Okay, super simple. Okay, required only very simple, lightweight materials, okay, in order to do it. All right, so the formula works very similar to the last one, except instead of having m and k under the root, now we have L and G under the root. Okay? And same thing, if I want to manipulate, I square everything and so on. All right. Okay, so we'll look at this example here. Okay, so what is the period of a pendulum located on a high mountain where the acceleration due to gravity is 9.71 meters per second squared if the pendulum is 1.55 meters long? So all we have to do, plug it into our formula. Okay, so 2 pi times the square root of 1.55 divided by 9.71 gives us 2.51 seconds. Okay, that's a pretty long pendulum, so it would take quite a while for that to go back and forth. Okay. Now, other terminology. This is Plumb Bob SquarePants. He lives in a pineapple under the sea. Absorbent and porous and mellow as he. You will now have that song stuck in your head. You're welcome. Okay, so the mass on a pendulum is called the bob. I don't know why, but that's what it's called. Okay, so if ever a question is referring to the pendulum bob, it means the mass on the bottom of the pendulum. Okay, that mass again is irrelevant, but we do need a mass there. Okay, otherwise there's nothing to accelerate. So every pendulum has a bob. Okay, doesn't always look like plumb bob, pendulum bob.
So if you didn't have that tape on there and you dropped the string would still do that though, right?
Yeah, there'd be enough mass in the spring, or sorry, in the string, but it wouldn't go well because the string is slack. It would go slack.
Yeah.
And you need that mass to keep keep that in there. Now, if you had a pendulum that was a rod, that would be different.
Right.
Okay, because the rod can't go slack, so the mass of the rod itself would then act as the pendulum. That's the ball. Yeah. In fact, I saw a video the other day of a guy who was on a swing that you could make go upside down. Okay, can you make a swing that's on chains go upside down with somebody in it?
No.
No, you can't. Like, it doesn't matter how hard you pump, you'll never get it to go because you'll lose the tension in the chains.
Unless what
right?
if you had someone in like a crane lift the person up really high and then drop them?
Well, you'd have to lift them to vertical,
Yeah.
and then they would drop
Oh.
straight down.
So what if you was like, there's no way you could possibly do that?
The only way you could do it would be to shoot them from a cannon from the bottom, so that there would be enough tension and that minimum speed for a vertical circle, right? Okay, to go around and not lose the tension in the string, in the chains. Okay, it's just not possible for anyone to pump a spring,
So how
a
did
classic
that-
swing that hard.
In the video you saw.
It was a rod, so there wasn't any worry of them falling back. The rod kept them the same distance from the center all the time, so they just had to keep pushing. So as they came through, they bent their knees, and as they went up to the top, they straightened, and then they fell back down and bent their knees. Just like pumping a swing, except you're standing on it instead of sitting in it, and it was a rod instead of chains. Yeah. And so they were able to actually make it go all the way around. it was a little bit, it like created some anxiety in me because the person wasn't wearing a helmet and they're, you know, they weren't strapped to it in any way, secured or anything like. See, this is what happens when you become a parent. You see the world in an entirely different way, and it's very unsafe. Yeah, it's very unsafe. Okay, you guys are still young and indestructible. You're not indestructible, but okay. All right, try this one. I want you to determine the length of a simple pendulum that will swing back and forth with simple harmonic motion and have a period of 1 second. Okay, and we'll assume that we're using normal 9.81 gravity. Okay, give you a minute on that one. All right, so on this one, what we have is the period, okay, 1.00 seconds, and we have G, 9.81 meters per second squared. Okay, big T equals 2 pi times the square root of L over G. So to get those out, I've got to square everything, so I will have T squared equals 4 pi squared times L over G, okay? And we are just looking for the length of that pendulum, so I'm going to multiply both sides by G. Okay, and then I'm going to divide both sides by 4 pi squared. Okay, that's going to leave me with L, so I just have to plug in my numbers. 1 squared times 9.81 over 4 pi squared. So 9.81 divided by 4 pi squared will do it. Come on. Okay, so that pendulum is about 25 centimeters long. Okay, 0.248 meters, okay, in length. What do we have? 3 significant. So 0.248 meters. Okay, is that a terribly difficult formula to use? Okay, very straightforward. All right, try that one. This one you're looking for G. So we don't know what G is on this planet, which would have made it very difficult to land there, but context aside. Okay. We know the length of the pendulum is 0.65 meters, and we know that the period of that pendulum is 2.8 seconds. So already, just looking at those numbers, this planet has less G than Earth. Okay. We just did a pendulum on Earth, okay, that had a period of 1 second that was 25 centimeters long. Okay, this is a little bit longer, but the period is way longer. Okay, all right. So we've got T equals 2 pi root L over G. Okay, so I'm trying to find what G is, so I'm going to square everything. T squared equals 4 pi squared times L over G, and then I'm just going to swap T and G. All right, so 4 pi squared times L over T squared. What do you suppose people forget to do on these questions more than anything else? Square T in their calculator. Yeah, they'll do all of this, but they'll forget to square it in their calculator. So just make sure you're squaring everything. Okay. So we'll have 4 pi squared times 0.65 divided by 2.8 squared. Oh, that didn't go well. All right, let's try that again. 4 pi squared. I did it again. 4 pi times 0.65 and divided by 2.8 squared. All right, so 3.27 meters per second squared is the acceleration due to gravity on this planet, which would make it which planet? It's about 1/3 of Earth. Mars, yeah. This is the acceleration due to gravity on Mars, approximately.
So, Mr. Coder,
Mm-hmm.
do your students usually do good on this unit?
Yeah, it's an easier unit. The problem with the exam on this unit is people are usually already getting kind of stressed about finals, right? Because it's close to the end of the semester. I mean, the rest of the stuff in the unit, yeah, it's pretty straightforward.
Isn't it 3.3?
Yes, it would be 3.3 because we only have 2 significant days. Okay, that's all I want to go over for today, but I want to talk to you about a couple of things. So there's like 3 weeks left of class. Okay, that's it. We're gonna need pretty much all of it to get done this unit. Okay, we usually have almost another week for this unit. Mr. Dickey's in the same boat. I talked to him yesterday and we can't figure out what happened. But we're a little short, but we'll be fine. Okay? Your unit exam, I will post the date for your unit exam next week for unit 4, so that you know when it is. Okay? And I will stick by that date. My suggestion for you guys starting now, okay, is that each night you should do a little bit of preparation. That does not mean for you to lock yourself in the room and spend 3 hours a day for the next 3 weeks studying. You definitely do not have to do that, nor should you. But what I'm saying is take 5 or 10 minutes each night and try a problem from another unit. You've got your digital workbooks, you've got the answers in the digital workbooks, okay? Try a vector addition question from unit 1. Try a projectile motion unit, question from unit 1. Do a Newton's second law problem from unit 2. Just do one a day, okay? Just pick away at it a little bit each night, and before you know it, it adds up to a lot of time spent studying. Right? Because everybody gets this idea, oh, I just need like 8 hours in the last 2 days before the exam and I'll be fine. Don't do that, okay? But if you do 5 or 10 minutes a day for the next 3 weeks, it'll be way more than 8 hours. Okay? And because it's spread out, you'll remember it better, and you'll know if you need to come and ask me questions about something. Okay? Rather than it's 3:30 in the morning and your test is at 9, and you're like, I need to ask Mr. Coderre how to do vector addition. You're screwed. There's no nice way to say it. At that point, you're screwed. Okay? Vector addition is part of 2 units, and you're not going to see me before you write your test. So, yeah, don't be that guy. Okay? You don't want to be that person. So pick away at it a little bit, and then you can pop in and see me at nighttime or at lunch or something like that. Just Mr. Coderre, I worked on a vector addition question. I'm not getting it. Can you help me out? No problem. Okay? Just take a little bit of time each night, and before you know it, you'll be feeling ready, and you will be ready. Okay? But it takes a little time management. That's why I pray for you to have time management. Okay? So yeah, that stuff is coming up. Monday morning, if you want to start your unit exam early, be here for like 10 after 8 or so, and I will give you your test and you can get started. Okay? For your test, calculator, pen or pencil. The formulas are on the front, so you won't have your formula sheet. Okay. All right, questions from you guys? Okay, we're done.